Hi, my name is Shahnawaz. This is the first lecture of lecture series on category theory. So, category theory actually takes a bird's eye view of mathematics. From high in the sky, details become invisible, but we spot patterns that were impossible to detect from ground level. For example, what do discrete topological spaces, free groups, and fields of fractions have in common? Or how is the least common multiple of two numbers like the direct sum of two vector spaces? So, we will discover answers to these and many similar questions, seeing patterns in mathematics that you may never have seen before. So, the most important concept that we are going to learn is that of universal property. The further you go in mathematics, especially pure mathematics, the more universal properties you will encounter with. So, like all branches of mathematics, category theory has its own special vocabulary, which we will meet as we go along. So, let us first define what do we mean by a category. So, a category is actually a system of um, related objects. The objects do not live in isolation. So, there is some notion of maps. Maps between these objects that bind them together. Uh, Now, categories are themselves mathematical objects, and with that in mind, it is, unsurprising that there is also a notion of maps between uh, categories. Such maps are called functors. Now, perhaps more surprising is the existence of maps between functors. Now, these maps are called natural transformations. So, we are going to learn these functors or natural transformation as we go along. But let us first define what do we mean by a category. So, we have a definition. So, a category uh, is actually a quadruple. So we usually denote category by fancy letters. So let us take the fancy letter A. So this category A contains a class of objects. So we say OB for objects and a class of morphisms or maps. So let us note that by home. And for each object we have the identity map and we have uh, the circle here which stands for the composition. So it consists of consisting of so first of all we have a collection OB of A. This is the objects of A. So second we have for each pair of objects, so for each pair AB of objects, we have a collection of maps. So this collection is denoted by home AB. Sometimes we write subscript here. We write fancy A here to emphasize that these elements, AB, they are the objects or of the category A. But here we do not need to write A here because we just have only one um, uh, category here. So this collection is called. So this is actually a collection of maps. or sometimes we call these maps as arrows or morphisms from A to B. Then we are done with OB, we are done with home. Now we have one here, and one stands for identity map. So for each object, say A in fancy A, we have an element 1 sub A, which is a morphism from A to A, called the identity map on A. And finally, we have the fourth condition, which is the for each A, B, and C, which are the objects in the category A, we have a function, and this function is from home BC cross home AB to home AC. Now this function goes like this. So it takes an element in home BC, let us take this element to be G, and an element in home AB, let us call that F. So it takes this element and it maps it to the function G composed with F. So this is called the composition. So this O is called the composition. So this is called the composition. Now these elements are, these are subject to the following conditions. These given four items, they are subject to the following conditions. So the condition one is given as, the condition A is the associativity. Now what it says if we have a morphism from A to B and a morphism from B to C, let us call that G, and say we have a morphism H from C to D, then we have so if we take the morphism H and we compose it with the morphism G and then compose this morphism with F, the same as if we first compose morphism G with F and then compose this morphism with H. So what it says, so um, I mean if we have object say A, let us write this here. If we have A, B, C, D objects here, and between these objects we have the maps. So this is the map F, this is G, this is H. So going from A to D is same as first go from A to B, then go from B to D via the map H composite G. So it is same as if we first travel the composite map G composite F. So that map takes us from A to B, A to C, Then we compose the map GOF with H, and that will take us from C to D. So these two maps, they should agree. And the condition B says that this condition is called associativity, and the second is called the identity law. And this law states that, so for each morphism, for each morphism F in the set home AB, in the collection home AB, we have uh, F composed with the identity map on A. So this should be equal to the identity map on B composed with G. So we have two objects here. One is object A, other is object B. So from object A to object A, we have the identity map. So this is IA. So from A to A, we have the identity map. Let us call this 1 sub A. And from A to B, we have the map F. So this composite map, the composite map, so this is from B. The composite map from A to B is here, F composite with 1 sub A. So this should be equal to, this must be equal to the F, which is the map from A to B. Similarly, here we have the identity map on B. Let us call that I1 sub B. So if we first go from, this is not G here, this is F here, sorry. So if we first travel A to B via the map F, and from B to B we go via the map identity on B, then this composite map, which is 1 sub B composite F, so this must be equal to the map F. So that means these two maps are equal. So this condition has to be satisfied. Then it makes sense. Uh, then the definition of a category makes sense. Now we have some remarks here. So remarks. So first remark is, so we often write object A in category A to mean that mean to mean that A is in the class OB of fancy. And we have the second remark. Let us call this first item. Let us call this second item. So for so if we have we mean by, so F from A to B, or an arrow from A to B. So this means, so we write this to mean this F is an element of home AB. So either you write F is in the set, or you draw these arrows like this. So third is that, so this was remark first. and this is the first item of remark first, this is second and third. And third is we often write GF to mean G composed F. So as a shorthand we write this notation here. So now we have second remark here. So if F is a morphism from A to B, we call A the domain of F and B the codomain of F. So we call A the domain and B the codomain of F. Finally, we have third remark. So third remark, I mean, we often speak of commutative diagrams. So we often speak of commutative diagrams. So for instance, uh, given some objects and maps, so let us suppose we are given objects A, B. Suppose we have object C here, we have object D and object E, and suppose we have a morphism here, say this is the morphism F, suppose this morphism H, suppose this morphism I, suppose this is morphism G, and this is the morphism J. Now to say that this diagram commutes, we mean, so then to say the diagram commutes, we mean, so one should note here, so to reach from A to A, we first go to B via the map F, and finally the map, finally from B to E via the map G. So one way to reach from A to E is first travel the map F followed by G. The other way to travel from A to E is first go via the map H followed by map I and followed by map J. So these are the two ways. One is GF, other is the map H followed by I and followed by J. So to mean this diagram commutes means that these two ways, these two paths, I mean these two maps are equal. So we mean uh, uh, so we say then to say the diagram commutes, we mean the map G composed with F is equal to the map J composed with I composed with H. So finally we have the fourth remark. So the definition of a category is set up so that I mean in general, for each string of maps, for each string, let us take a string of objects and morphisms. A0 goes to A1 goes to up to AN. So this is the map F1, this is the map F2, and finally this is the map Fn. So for this string, uh, we have it is possible to construct exactly one map. So it is So we have the string of maps. So for this string, one should be, one, it should be possible that to construct exactly one map. So it is possible to construct exactly one map. Say, the map from the starting object, which is a node, to the last object, which is an, and this is the map. First we have to go via map f1 followed by map f2 up to fn. Now let us mention some examples of categories. So we have examples. So these examples are the categories of mathematical structures. So we have the categories of mathematical structures. So first we have, the first category is the category set. The category set. So we'll write this as bold so that this would imply this is a category. So this is the category set of all sets. So now this category, it is objects are sets, the maps are all set maps, and the functions, morphisms are all set functions from object A to B. So its objects are sets whom AB, if A and B are the objects, then whom AB is the set of all functions. So the usual functions from a set A to B. So from usual functions from A to B. And we write one sub A is the identity map on A, is the identity map on A, and the composition in this category is the usual composition of functions, and the composition in the category is the usual composition of functions. Let us write one more example. So this is the category set, and then we have the category group. The category group. So this is the category of groups. So here the objects are groups and the morphisms are group homomorphisms. So it is objects are groups and the morphisms are the group homomorphisms. So here one should note that the identity on a group is the anti-homomorphism. Then we have the category ring. So this is the category ring of all rings. So similarly here the objects are rings and the morphisms are ring homomorphisms. So its objects are the rings. So its objects are rings and and morphisms are ring homomorphisms. Then we have the category top. The category top of topological spaces. So here the objects are topological spaces and the morphisms are continuous maps. So its objects are topological spaces and morphisms are continuous maps. Then we have in the category of vector spaces over some fixed field K. So the category vec of K. So this is category of vector spaces. So its objects are vector spaces over the field K and morphisms are the linear maps between vector spaces. And the morphisms are the linear maps or linear maps. Now we have the definition of isomorphism. When we say two objects in a category are isomorphic. So we have this definition here. So let us suppose A is a category and let us pick two objects in the category. So let A and B be two objects in the category. We say a map, I mean a morphism, say F from A to B. That means this F is in the set home AB. So this is an isomorphism. Uh, if there exists a map, if there exists a map G, I mean a morphism from B to A, such that if I look at the composite map, I mean G composite with F, so it is equal to the identity map on A, and the map F composite with G, it has to be equal to the identity map on B. So in this situation, we call G the inverse of F. So in this situation, we call G the inverse of F, and write this G is F to the power minus 1, and vice versa. So if there is an isomorphism from A to B, we say A is isomorphic to B. So if A, if there is an isomorphism between A and B, we say A is isomorphic to B. And we write this statement with this symbol: A is isomorphic to B. Now let us do some examples. Let us take the category set. So the isomorphism in the category set is just a bijective map. So any two objects in the category set are isomorphic if and only if they have the same size. So the isomorphism in set are exactly the bijections, and objects. So hence object A is isomorphic to object B if and only if size of A is same as size of B for any objects A and B in A. Let us take the second example. So the isomorphism in the category group, the isomorphism in the category group are exactly the group isomorphisms. So two groups in the category group are isomorphic if they are isomorphic as groups. If there is a group isomorphism between them. Let us take the third example. Now the isomorphism in the category of top, the category of topological spaces, are the homeomorphisms. So the isomorphism in the category top are exactly the homeomorphisms. So, unlike sets and groups, a bijective map in top, the category of topological spaces, is not necessarily an isomorphism. So, unlike the category set and the category group. A bijective map is not necessarily an isomorphism. Here is a here's an example. So a classical example is the map. So let us take two topological spaces. One is the topological space 0 1. So it has, the subspace topology on R. This inherited space topology from the usual topology on R. So from this object to the object, set of all complex numbers with modulus 1. So this map is given by, so we take an element t here. So this t is mapped to e to the power 2 pi I t. So one can notice here that this map is bijective continuous, but this map ceases to be a homeomorphism. So which is bijective continuous, but not an isomorphism, since it's not a homeomorphism. Since the map is not a homeomorphism. So one can note over here, this is the closed open interval. So this is 0 to 1. So this is 0 here, this is 1 here, and this is the circle here. So they are not homeomorphic, because if we look at this set over here, so it is first fundamental group is, so it is trivial, it is 0. And if I look at the fundamental group of this topological space, so this is the circle here, so it is isomorphic to the group of integers. So two topological spaces, if they are homeomorphic, then they are necessarily their fundamental groups are necessarily isomorphic. So we can see over here, the first fundamental group of the space 0 1, which is trivial group, and here we have the uh, mm, the first fundamental group of S1 is this circle, the group of integers. So one can note over here, the group of integers is not isomorphic to the trivial group. That means these two spaces, they cannot be homeomorphic. So these two spaces not being homeomorphic means that these two objects are not isomorphic.